Look at the volume of material moving through our industrial systems. Every single year, humanity extracts and consumes raw materials on a massive global scale. This flowchart maps out the linear economy. We take raw inputs from the earth, make products, and eventually dispose of them. As of 2024, this disposal vector represents over 100 billion tons of material discarded annually. To an environmentalist, that number represents severe ecological damage. To an engineer, a 100 billion ton open loop is a catastrophic failure of process efficiency. This is the physical reality of an open loop system. Valuable mass and energy are permanently lost at the end of the line. Waste represents a mathematical design flaw in how we construct global supply chains. Solving it is a primary engineering mandate. This closed-loop diagram outlines the circular economy framework. First, you engineer the system to design out waste entirely. Second, you build systems to keep materials continuously cycling. Third, any returning material must regenerate natural systems, not pollute them. To execute these principles, industrial engineers operate across three specific scales. First, internal recycling. Second, industrial symbiosis. And third, waste valorization. Mastering these three scales achieves true resource efficiency. They form the core pillars of clean technology. This pyramid charts the hierarchy of resource recovery. At the absolute top, focused on prevention and reduction, is internal recycling. This is the first line of defense, where a facility captures and reuses resources strictly within its own boundaries. The motivation here is direct process optimization. By looping materials back into the system, plants lower their raw material consumption and immediately cut their operating expenses. The semiconductor industry requires massive volumes of ultra-pure water to manufacture silicon chips. Intel Corporation treats this heavy usage as an opportunity for high-volume recovery. Instead of discharging effluent, they deploy advanced unit operations like reverse osmosis and ultrafiltration to strip impurities from the used process water. The result is precise and measurable. In certain facilities, up to 80 to 90% of the process water is successfully reclaimed and looped right back to the plant's inlet. Mass recovery is only half the equation. Heavy-duty operations, like cement manufacturing at Lafarge-Holcim, tackle the problem through energy recovery. This process flow shows a waste heat recovery system. Cement kilns generate massive high-temperature exhaust. Instead of venting it, the gas is diverted. This captured thermal energy drives a steam turbine, converting waste heat into electricity, which feeds back to power the plant. Internal recycling rewrites a facility's economic profile. An expensive waste stream is optimized into a reliable internal utility source. Internal loops have thermodynamic and chemical limits. When a facility produces a byproduct that it absolutely cannot reuse internally, engineers have to look outside the factory gates. This is level 2, industrial symbiosis. It operates as a collaborative network between distinct industries under one strict rule: waste equals resource. This network map outlines the Kalundborg industrial symbiosis in Denmark. It begins with a central power plant. Excess steam and water are piped directly to neighboring oil refineries, requiring thermal inputs. In return, local agriculture feeds leftover biomass inward to fuel the grid. This networking solves massive liability issues. Coal power plants generate thousands of tons of problematic fly ash. Traditionally, this ash sits in landfills, but chemically, fly ash is an excellent structural additive. Through industrial symbiosis, it is transported to a local cement manufacturer to replace virgin raw materials. Even the sulfur emissions scrubbed from the plant's exhaust yield waste gypsum, which is recovered and piped straight to a dedicated gypsum board plant next door. By forcing independent plants to operate as a single integrated macroorganism, industrial symbiosis achieves near-zero waste while significantly boosting regional profitability. This matrix outlines level 3, waste valorization. This is the engineering practice of upgrading disparate low-value waste streams into high-value chemicals, fuels, or materials. The core engineering challenge is selection. You must match the precise processing pathway to the exact chemical profile of the waste. Consider the agricultural sector in Southeast Asia, specifically the Malaysian palm oil industry. The extraction process leaves behind massive tonnages of structural biomass, primarily empty fruit bunches and mesocarp fiber. Because of its high carbon content, Engineers subject this tough biomass to intense thermal and chemical valorization pathways, like pyrolysis and gasification. What enters the reactor as agricultural waste emerges as high-value commercial outputs: biochar, activated carbon, and biofuels. The food and dairy industries use a similar approach to demonstrate physical and chemical valorization. Cheese production yields massive quantities of liquid whey. This was once a highly problematic and polluting waste when discharged into waterways. Now, the whey is isolated and processed. By extracting the remaining nutrients, facilities convert that pollutant into premium sports protein isolates and high-grade infant formula. Valorization rewrites the economic equation of an industry. It transforms a severe disposal penalty into an entirely new, high-margin revenue stream. We've seen how multinational corporations and entire industrial regions optimize their mass balances, but the exact same engineering principles apply at the local level. If you are an engineering student at Universitas Diponegoro, you are surrounded by active mass balances every day. Take a closer look at a high-volume processing facility located right in the middle of the university campus, the bustling student cafeteria. This flowchart tracks the facility's outputs. Every day, it generates 3 continuous, unrecovered streams: organic food waste, complex wastewater, and used cooking oil. The challenge for engineers is clear. How do you close these loops right here on campus? Which valorization pathways do you select? Do you design an anaerobic digester to capture biogas from the food waste? Do you set up a catalytic conversion system to turn the cooking oil into biodiesel? The linear model of extracting, using, and dumping 100 billion tons of material a year is an obsolete system. It can no longer be sustained. The global transition to a sustainable circular economy relies entirely on the precise, optimized systems that you will design next.